Transients in capacitive network. The charging phase. Any capacitive network can be classified into two phases, the charging phase and the discharging phase. Each of these phases can be further classified into two periods, the transient period and the steady state period. The transient period basically defines the period of time during which charge is being deposited on the plates of a capacitor. Now, let us consider this circuit. Initially, when the switch is open, the current through the circuit is 0. Hence, the potential across the capacitor will also be 0. When the switch is closed, current will start to flow through the circuit. In other words, charge is being deposited on the plates of the capacitor. As a result, the voltage across the capacitor will start to increase. Now, if we represent this by means of a graph, then it will look like this. The y-axis represents the voltage and the x-axis represents the time. The voltage across a capacitor will increase exponentially. Now, you might ask that how long will the voltage increase? The answer is the voltage across the capacitor will rise up to the point at which Vc is equal to E. The time period required by the capacitor to reach this voltage E is known as the transient period. That is from 0 up till this point. The point where it becomes equal to E, Vc becomes equal to E, is known as the transient period. When the voltage across the capacitor becomes equal to E, it is said that the capacitor has reached the steady state. When Vc becomes equal to E, the voltage across the two terminals of the resistor are equal. Hence, no current will flow through the circuit. As a result, no more charge will be deposited on the plates of the capacitor. And thus, the capacitor will maintain a constant voltage of E across its terminal, that is the steady state. This graph can be defined by the expression Vc equals E times 1 minus E to the power minus t by tau, where E represents the source voltage, the lowercase letter t represents time in seconds, and tau is a variable which is expressed by the formula tau equals RC. We know that R equals V by I and C is equals to Q by V. Now, if we substitute I with its formula Q by T and cancel out all the common variables, we'll see that tau has a unit of seconds. The universal time constant chart is shown over here. The x-axis represents the time t and the y-axis represents the signal value. Over here there are two curves. This curve is the exponentially rising curve and this curve is the exponentially decay or exponential fall curve. The exponential fall curve is represented by the expression y equals e to the power minus x, and the exponential rise curve is represented by the expression y equals 1 minus e to the power minus x. Within the first time constant, that is 1 tau, the rise curve will reach a value of 0.632, that is 2/3 of the actual value, and the fall curve will decay 0.368 or 1/3 of its maximum value. In order to reach the maximum value, the rise curve usually takes 5 tau, and to reach the minimum value, the fall curve usually takes 5 tau. The voltage across a capacitor in a DC network is essentially equal to the applied voltage after 5 tau constants of the charging phase. That is, it takes 5 tau time constants for the voltage across a capacitor to reach from 0 to maximum supply voltage E volts. The transient or charging phase of a capacitor has essentially ended after 5 time constants. That is, after 5 time constants, which is 5 tau, the capacitor has entered the steady state period. Now, as I have mentioned earlier, that when the voltage across the capacitor increases, the current flowing through the circuit decreases. The current decreases in an exponential manner. The equation for the current is IC equals E by R e to the power minus t by tau. The graph to represent the current, the flow of current, is this one. This is the exponential decay curve for the current flowing through the circuit. The maximum value of the current is E by R. This current is achieved or obtained at the point the switch is closed. The current of a capacitive DC network is essentially 0 amperes after 5 time constants of the charging phase have passed. It is also important to recognize that during the charging phase, the major change in voltage and current occurs during the first time constant. The voltage across the capacitor reaches about 63.2% or about 2/3 of its final value, whereas the current would decrease to 36.8%, about 1/3 of its peak value during the first time constant, that is 1 tau. A capacitor can be replaced by an open circuit equivalent once the charging phase in a DC network has passed. That is, when the voltage across the capacitor reaches the maximum supply voltage of E volts, then the voltage in these two nodes will become equal. This is because at that point of time, the capacitor can be replaced by an open circuit equivalent. And hence, the current flowing through the circuit will become 0. The moment this switch is closed, a capacitor has the characteristic of a short circuit equivalent. Hence, the maximum current flowing through the circuit at that point of time is equal to E by R. The voltage across a capacitor cannot change instantaneously. It changes exponentially. Hence, the current flowing through the circuit also decreases exponentially during the charging phase of a capacitor. The voltage across the resistor can be determined by using Ohm's law in the following manner. VR is equals to IR. Now the resistor and the capacitor are connected in series. Hence, IR will be equal to IC. Thus, VR will be equal to E by R e to the power minus t by tau times R. This R and this R cancels out each other. Hence, VR is equals to E to the power minus t by tau times the E, voltage. Now, e to the power minus t by tau basically represents an exponentially decaying curve. When plotted, VR equals e to the power minus t by tau against time. This is the graph that we will get. Within the first time constant, that is 1 tau, the curve will decay 0.368 times of E.